Hi, my name is Avi Perlman, and this is Lab 5, Faraday's Law and Magnetic Braking. The purpose of this lab is to provide a real-world example of Faraday's Law by observing a magnet falling through a conductive tube of aluminum foil. Additionally, I utilize Python to model this interaction computationally and compare the computer-generated results to my empirical results. Ultimately, I found that the aluminum foil slowed down the falling magnet. I found experimentally that it took the magnet 1.32 seconds to fall through the tube, while it took 1.29 seconds computationally. The central physics principle behind this lab is Faraday's law, which relates a time-varying magnetic field to a Curly electric field, whose path integral around a closed path provides an EMF that can drive current. In this lab, the falling magnet is the source of the magnetic field, and the induced current travels around the circumference of the tube of foil. We also make use of the Biot-Savart law to find the magnetic fields of the bar magnet at various locations. Lastly, this lab utilizes Newton's second law, which states that the acceleration of an object is dependent on the force exerted upon it and its mass, as well as Newton's third law, which states that every action has an equal and opposite reaction. We can't use a ferrous tube for this experiment because ferrous tubes contain iron and could potentially become induced magnets, which would in turn interfere with the falling magnet. The process of this experiment is fairly simple. First, I marked the north pole of the bar magnet by utilizing a magnetometer smartphone app. Next, I held the aluminum foil tube vertically and had my friend record a video of me dropping the magnet through the tube, ensuring that the full tube was in frame. I reviewed the footage and determined how long it took for the magnet to fall through the tube. After doing this 5 times, I averaged the amount of time that it took for the magnet to pass through the tube. Here are the results I observed from the experiment. I found that it took the magnet an average of 1.32 seconds to fall through the aluminum tube. While conducting the experiment, it became apparent that dropping the magnet through the aluminum foil tube caused it to fall more slowly than it would have in free space. Next, I created a computational model in GlowScript utilizing Python. The link to this code is available in the description of this video. First, I ensured to create variables for the necessary physical constants. Next, I created variables for the geometry of the aluminum foil tube. After that, I created a function called dipole-B, which takes in the arguments mu and r and returns the magnetic field of the bar magnet. I also created a function called calculateDfluxDT analytic, which has parameters magnet and ring and returns dfluxDT through each ring due to the falling magnet. I also created a variable for the vector force of gravity. After that, I created a function to calculate the magnetic force from the tube on the magnet and place the results in a corresponding F magnetic vector. Finally, I utilized Newton's second law to update the magnet's velocity and position. Here's what the output of my code looks like. As you can see in the velocity versus time graph, the magnitude of the velocity initially increases before it decreases. At the end of the tube, the magnet speed again begins to increase. The model predicts that the magnet would remain in the tube for 1.285 seconds, which is slightly shorter than the 1.32 seconds which I found experimentally. This could be a result of human error in reviewing the footage. If the resistivity of the conductor were reduced as close as possible to 0, the induced current in the tube would be larger due to Ohm's law, which would in turn cause the magnet to take longer to fall through the tube. If the resistivity was exactly 0, it's possible that the braking force would cancel out the force of gravity and the magnet would stop falling altogether. If holes or slots were cut into the tube, the magnet would fall through the tube faster because the flow of the current through the tube would be disrupted.